In this video, I'm going to walk through the results from the assignment from yesterday, where I had you guys use the reg command and then the areg command in STATA on your particular sample of midshipman data. This is an exercise in seeing what happens when you don't control for unobserved heterogeneity versus when you do. So we start out with this model, and the way this model is written is it's ignorant or it ignores unobserved heterogeneity of each student. And STATA doesn't know that unobserved heterogeneity might be a problem. So when you run a regular OLS regression, STATA is going to give you results no matter what. So we'll see something like this with the reg command. Typical results. You can interpret these as you normally would, right? We have semester credit hours, varsity athlete, and the female dummy variable. And in this particular case, the semester credit hours are statistically insignificant, while the dummy variables are both statistically significant. Notice too, the R squared is super low in this regression model, even though the model overall is statistically significant according to the p-value for the F statistic. Notice also that in contrast to the samples that you guys estimated with, which each had 1,000 observations, here I'm using the entire sample of midshipmen, and there's actually 19,384 observations. Okay. The problem with those results is that if the unobserved uniqueness factor is correlated with varsity, the number of credits, or gender, any of those independent variables, then those estimates that we just looked at are biased, the standard errors are incorrect, and that's what I like to call the double whammy on your regression model. Everything is wrong. You can't move forward. You have bogus results. So to control for that uniqueness, we need to recognize it exists, but we don't have data on it, let's say, right? It's the intangibles of a person. We don't have data or a variable to control for it. But we can write the model in this way, where A represents that unique factor. And in the first go around, we can use dummy variables for each student to control for A. So in the sample that you guys used, there are 250 students. So that implies you need 249 dummy variables. And that will also mean that you're estimating 253 parameters, right? It's those 249 dummy variables plus the other betas in the regression with those 1,000 observations. So that's something to keep in mind. So to do that, we can use the areg command. And what the areg command is doing is it's telling STATA to create dummy variables for all those persons in your sample, all 250. And the gist is that's too many coefficients to look at. So it's doing it behind the scenes. So we don't see the results for those dummy variables. We just see the results for the main variables in the model: semester credit hours, varsity athlete, and female. But the areg command, again, it's applying the dummy variable for each student in the sample. Now, in this particular case, there's over 4,000 students, so that's why it's the number of categories is 4,846. Notice too that the female factor, the gender variable, the dummy variable, was omitted because of collinearity. This is what I emphasized in the lecture videos on panel data. Since the female dummy variable is unchanging for each female over the sample period, and here there's 4 semesters in this data set, that's a fixed time invariant factor. So that's going to be correlated with the dummy variable for each midship. And that is why female drops out of the equation. Remember, when you use fixed effects, like we are here using the dummy variables, any other factor in your model that's time invariant drops out. Now, varsity athlete is still in the model because over these 4 semesters, there's enough students who were varsity athletes, but then stopped being varsity athletes. So there's some time variation in that varsity athlete variable, even though it's still a dummy variable. All right. Notice a comparison to the last regression where we did not control for the unobserved intangible factor. Now our coefficient values are a little different. We don't have any results for female, like I just said, and both things are statistically significant. And also, notice how big the R squared is versus the previous model. Now, if we put those side by side, we can see the big difference in the results. The biggest takeaway is that semester credit hours has a negative coefficient versus the virtually zero coefficient in the OLS results. And now it's statistically significant. The varsity athlete variable, it doesn't change a lot, and it's still statistically significant. So the biggest change is that semester credit hour variable. So what you can conclude from the OLS results is that the coefficient in particular on semester credit hours was biased because we did not control for the unobserved heterogeneity. We can conclude now with the LSDV results, the least squares dummy variable results, using the areg command, that these results are unbiased. Now let's make a few points with respect to the method of using the areg command, which again is implementing the least squares dummy variable method, versus the within method. The within method is discussed in chapter 14 of Wooldridge, and it's in the latest video, video 19 in our video lecture series. So typically we can use fixed effects command in STATA, which is the within method, and I'm going to actually show you how to do that in a second, even though we didn't do it on our assignment. And for big enough sample sizes, the fixed effects within method will give the same results as the least squares dummy variable model. But with the least squares dummy variable model, if we only had 2 time periods, you'd have 500 observations to estimate 253 betas. And these results are likely insignificant. So we'll use the within method. And I'm sorry, there's a typo there in that last bullet. So the within strategy, as I discuss in lecture note 13 and video 19, we're still estimating this general fixed effects equation where the A sub I is still capturing or standing in for those individual factors for each student, but we're going to use a different method than using dummy variables. And the command is, as it's seen here, the xtreg command, right there. It's just, again, like STATA likes to do, it slightly modifies the reg command. And then the key here is that this FE stands for fixed effects. Everything else is the same. So when we use that command, we get a slightly different looking layout from STATA, but the key is we still have the same number of observations, same number of groups, and coefficient estimates for those variables. Female again drops out for the same reason as the LSDV model. And notice that these are the exact same estimates as we got before when we used dummy variables to control for the fixed effects, the time invariant effects, as opposed to the within estimator. So what this means is that fixed effects methods, whether it's the least squares dummy variable model or the within method, they will control for that unobserved factor. The key is that unobserved factor does not change over time, and this helps us avoid omitted variable bias. You can use the least squares dummy variable model, the first difference transformation, or the within transformation. The most common is the within, since you can use it on short or long panels. And that is the end of our talk. Thanks.